by Trey, the sophomore at Carnegie Mellon. I should point out that this is joint work with Angela Patini and Jeremy Johnson at the MSRIL summer program. If I remove their names so I can know what it's like to have it all for myself. So a little bit about the talk. So we'll do some preliminaries, background history, motivation, and the main result. Okay, right, I don't have to keep looking back. So first we should talk about modular arithmetic. So suppose you have an integer n, then we call this group z mod nz, and it's basically the set of integers modulo n. So these integers are like the remainders you get when you divide a number by n, basically. So for example, if you let n equals 3, then 22 is 1 mod 3, since 22 is 3 times 7 plus 1. In particular, we say like a is congruent to b mod n if n divides a minus b. It's another way to think about it. So we'll be interested in z mod pz, where p is always going to be a prime number. And particularly, we call this the finite field of p elements, or fp. Yeah, that's just a different notation. So now we could define reducing integer polynomials modulo a prime number, right? So suppose you're given a polynomial f of x, and it's written in your standard way, like this. And basically, the way you reduce this polynomial modulo prime is, well, you just take all the coefficients and just reduce it mod p in this sort of way we defined modular arithmetic earlier. So in this field, like fp adjoint x, f of x becomes basically this. Like the coefficients are, members of the equivalence classes modulo p. So an example, so you can see this concretely, is so f of x, we have this polynomial and we want to do a mod 5, and 5 the prime, but that's not important in this example. Then you take each number and you say, okay, 18 divided by 5, the remainder is 3, 14, the remainder is 4, etc. And so that's our polynomial that lives in this this different ring. So some background. So I guess number theorists for a really long time have been interested in these sort of Diophantine equations, or basically these, you have some polynomial and n variables, and you see, okay, when is it 0? And particularly they're interested in the integer solutions. So one famous one is from Maslow's theorem. This is a famous Diophantine equation. And it says that x to the n plus y to the n equals z to the n doesn't have integer solutions for n greater than 2. So Fermat actually claimed he had a proof for this, but he didn't. And he said he didn't have room to write it, but he definitely didn't have the proof. But one easier example is the Pythagorean triples, right? This is sort of a form of this general equation for n equals 2 case. And you might remember those from high school, thinking about, okay, like 2 sides of a right triangle, you add the squares and they make up the third side, right? So there's sort of this idea of having like a geometric intuition for these number theoretic problems. And there's a picture from Ma, for fun, I guess. So another problem we could talk about is the congruent number problem. So we say n is a congruent number if n is equal to the area of a triangle with rational side lengths. So, for example, this triangle, each of the side lengths are rational numbers, so it's just like a number of fractions, basically. And if you take the area, 20/3 times 3/2 times a half, you get the area of 5, right? And so, one such proposition is that, okay, well, the number n is congruent if and only if the Diophantine equation y squared equals x cubed minus n squared x has a point xy where x and y are rational, right? So this is pretty cool because, okay, so you have this geometric problem, right? Like, okay, when do I have a triangle that has an integer area with rational sides? But we can sort of translate that problem into a number theory problem in a Diophantine equation. Or we could, once we translate it to that number theory, we could translate it back to geometry. And so now we have an elliptic curve. So this actually defines an elliptic curve. If you have some equation like y squared equals like x cubed plus that's an elliptic curve in Weierstrass form. And so you can study the rational points on elliptic curves because they're very easy to study, well, not easy to study, but they're very interesting to study because they follow a group law. So the congruent number problem is still open, but there's a theorem, Tunnel's theorem, that sort of like gives you sufficient things you need to know if n is a congruent number, but it relies on the Bertrand-Swinnerton-Dyer conjecture being true. And this is one of the 7 millennial problems. So, I mean, that's pretty heavy stuff for just this problem about, like, okay, when are my triangles, integer areas? So some more background. And then André Weil comes along. He's a French mathematician. And he writes this really seminal paper on the number of solutions of equations in a finite field. And he starts to really like play around with this idea of interplaying number theory with geometry and sort of trying to, I guess, counting the points on these like curves over finite fields, for example, an elliptic curve. And so one of the most important things that came about, and this is partly due to the Weil conjectures around the 1940s, is the Hasse-Weil bound, which was landmark in bounding points on these curves, right? Because if we can sort of bound the curves, that gives us bound the number of points on a curve, that gets us one step closer to counting the number of points on a curve. And so the bound is, okay, if C is a curve with genus G over finite field FQ, so here Q is a prime power, and we call this thing the number of points on C over this finite field. And we say that, okay, well, the number of points isn't going to be that far off from Q plus 1, right? That's basically like, and this is like the sort of error term. So that's a big deal. Like that was a pretty important thing, and it's really it's really remarkable.
Is that ever equal?
Excuse me?
Could that inequality ever be equal?
Yeah, it can be equal. I can't think of a specific example off the top of my head. Yeah, can it not be?
I don't have one in mind either.
Let's see.
Or could the constant, this TG, be any better? I'm curious. Don't spend time on it.
Can it be any better? So I'm pretty sure this is the best known bound. I mean, the idea basically comes from, like, okay, in a finite field with p elements, I might have, like, there's sort of p minus 1 elements there. And from, like, quadratic residues, we know that about half of them will be squares. But then you sort of have, and if you're working in a field, you sort of have this, there's symmetry over the x-axis. So a negative value and a positive value can get you the same square, because negative square is positive square. So then you have like, you have twice that many values. I mean, the bound is, I guess I'm not sure if there's a better bound, but I think equality does hold in a probably simple case that I'm not thinking of right now. Yeah, that's a good question. Anyway, so this basically, so what is a genus? You don't really need to know that much about it. Just that, look at it, right? This is the number of holes something has. Okay. So in particular, an elliptic curve has genus 1. And so one very important thing is the Mordell conjecture, which is like every curve with genus greater than or equal to 2 can only have a finite number of rational points. It's now known as Falting's theorem, which was proved in 1983. And this is sort of important because what it's saying is like, okay, so an elliptic curve, its genus is 1, so that's like less than 2, so it can have an infinite number of rational points. And that becomes pretty important if you want to count points on curves. So now we're going to do an example of root counting. So if we consider the integer polynomial f of x equals x squared plus 1, we know it has no solutions over the integers, I mean, let alone the reals. If we set it to 0, it has no solutions. However, if we look at it in mod 5, we see that x equals 2 and x equals 3 are two such solutions, because 2 squared plus 1 is 0 mod 5, and 3 squared plus 1 is 0 mod 5. But what about if we look at z mod 25z? And this is really like the heart of the problem we were working on. I mean, a lot of that was just some cool background, but it'll actually motivate some things. But anyway, if we look at like z mod 25z, we see again that we have two solutions. And you can see that, aha, these are both multiples of 25, so therefore I have a solution in this ring. And in particular, so I guess these solutions correspond to the points you have, and that's where the idea of counting these like rational points on curves comes from. And so there are two sort of routes, I guess, for counting roots. So one of them is let p be a prime for any pair of integers md greater than 0 and f in dp adjoint x1. Basically, that means you just have a polynomial and d variables over z mod p. And then we denote nm of f that's going to be a generating function that counts the number of roots to f equals 0. And so basically the Augusta-Poincare series, this is the generating series for nm of f. And so basically, I mean, this might look a little intimidating, but it just means that, okay, if we know that nm of f is the number of roots to f for some m, then we can encode those values in a generating function and assign sort of each of them, just assign it to the variable. And then, so what we're interested in is we want to pick out n2 of f, because n2 of f is going to be the solutions to f equals 0 for z mod p squared. And we want to work with p squared. And particularly we want to work also when d equals 1, right? Because we're working only in one variable. So this gives us one route to count solutions to f equals 0 mod p to m. Here's the problem. Like, if you want to get that coefficient, that involves the resolution of singularities, which is this really like high-level stuff in algebraic geometry, which, you know, is hard, but in particular it's computationally hard. So it takes exponential time. And one important thing about doing problems in number theory is you want to make sure like you can determine the answer efficiently, and you don't want things to like take a long time. So some troubles is, so in talking about the history, we've seen that a lot of these mathematicians have sort of used geometry to develop some intuition about these problems and help them solve them. But working with one variable polynomial sort of eliminates some of that geometric intuition that we have. So I guess the main point of all this is like, we'll give a formula for the number of roots f equals 0 mod p squared. So that's like that second term in the generating series. And we'll show that, okay, like, it can be found in a polynomial time algorithm. And when you're talking number theory, like, that's good. So I guess, so we should talk more about some of the difficulties. So like, what is the difference between all these things? And so the key difference is division is defined in z adjoint x and ft adjoint x. But when we go into p squared, we lose the unique factorization. And so I guess the easy way to see this is with an example. So usually, like, when we work with the integers, x plus 3, like, that's all it is. That's all it can be, right? But sort of, there's another way to think about it. Like, if you expand it and reduce it mod 9, then you have this different factorization. And so these factorizations are not unique. And so you can run into some problems. Also, we need to discuss, you know, multiplicities. And when I say multiplicities, what do I mean by that? So if f of x is this polynomial, basically, okay, this factor appears once. So 1 is a root, and 1 has multiplicity 1. 2 and 3 have multiplicity 2. I mean, it's just how many times it appears. And 5 has multiplicity 4. And then we have this sort of thing in the end that doesn't really factor that well. And so one assumption we're going to make is assume over ft adjoint x that we can factor f like this. And then let alpha 1 through alpha m be all the roots of multiplicity. Then we could define fi to be this sort of polynomial, where we take all the roots of multiplicity I and just write them as linear factors. And so in total we can write f like this, where it's a product of all the roots of the linear factors of the roots of multiplicity 1 and then multiplicity 2 and so on until you run out, and then you just have some junk on the end.
So I assume if we have no roots of multiplicity I, you just define fi to be 1.
Yeah. So as an example, like we can see this, like f1 would be x minus 1 because that's the linear factor of multiplicity 1. F2 would be x minus 2 times x minus 3. F3 would be 1. F4 would be x minus 5 because it appears 4 times, and then the g we attach at the end is just this thing that can't be factored in F7. Okay, so, and then we could write our f of x sort of like this. Yeah, and so I guess the main result that we get to is that, okay, let f be in z adjoint x without 0 have degree d, and for any prime p, let f be this polynomial that we find this way as the product of these linear factors raised to some power. And so that's this unique factorization in z mod p, z adjoint x. And it's important to note that, okay, g doesn't have roots in z mod p adjoint x, right? G is the stuff at the end that can't be factored. And so for any I, fi is monic and splits completely into distinct linear factors. That's just what we're saying before in this example, right? Like you can split them into just linear factors. And for any I not equal to j, the GCD of fi and fj is 1 in z mod p z adjoint x. That basically means like we're not going to have repeats, right? We're not going to have an x minus 2 here and x minus 2 here, right? Because that wouldn't really make sense because then the multiplicity wouldn't be correct. And this is a long definition, but anyway, you have to define t as 1 over p of f minus the way you've written f in z mod p z. And what that basically does is it sort of gets rid of the extra terms that you might have because f in z mod p zx, right? You can have some multiple of p, like you can add some multiple of p to that, and it won't be like, it'll be the same thing once you reduce it, but that sort of corresponds to like infinitely many polynomials, because you could just add a factor of p, right? So that really takes care of that. And then if we define h2 to just be the GCD of all of those linear factors with multiplicity greater than 1 and t, so the product of those and t, then this theorem says that the number of roots of f in z mod p squared is exactly the degree of f1 plus p times the degree of h2. And I think that's pretty neat. And so I'm not gonna, okay, so I guess I'll talk about the complexity. So this, like I said, it could be computed in deterministic polynomial time, and it's polynomial in this value, d plus size of f plus the log of p. And so I'm not going to go into too many details about the proof, but I should note that the main thing that the proof uses is Hensel's lemma. So if f is a polynomial in z adjoint x, and I tell you, okay, f of r is 0 mod p, so I give you some root in mod p, and I tell you that the derivative is non-zero, then you can guarantee a unique root mod p squared, right? So that is like if r is a root of multiplicity 1, then r lists to a unique root over z mod p squared. And the reason why multiplicity 1 is because, okay, well, the derivative is non-zero. And so his listing lemma is, okay, let f be a polynomial in z adjoint x. If I tell you that r is a root mod p and the derivative is 0, then I can generate a lot more roots by adding multiples of p to r. And so this gives us a way to lift the sort of degenerate roots. And so this lifting is going to occur sort of p-fold. And so if you look back at the theorem, like that's where this p times like everything with a multiplicity greater than 1 comes from in our root count. And yeah, so that's it. So I'd like to thank NAM, Dr. Goins, Dr. Blackman, and Medgar Evers College for hosting this. And hope you enjoyed the talk.
We have time for questions.
Well, a lot of what you said here, well, the last theorems at least, work for polynomials over one variable. But of course, there are versions of Hensel's lemma for any number of variables, any number of polynomials. So do you have an idea of maybe whether a similar result like this would work if you had, say, like what you showed before, a polynomial in d variables?
I think a similar idea could work if we look at multiple variables. I think right now the main interests that I've been working on for like research, for current research, is okay, we have it for p squared, but can we generalize for p cubed, and so on. And that's the part that's really hard. So I haven't given much thought to like the multivariable case, because I still want to like figure out this one variable case, because that should be easier to like figure out. But if you try to look at it for p cubed, because we conjectured a lot of like similar formulas, like you would think, okay, maybe like for p cubed there's just a factor of p squared in this like equation. You just add p squared times something. It actually gets much more complicated than that, and you have to deal with like, so one method we tried was using a Tech-Muller list, which seemed promising, but so far has not gone where we would have hoped. But yeah, that could be another line of attack to try to find out more about this problem. Yeah. Okay. Yes.
I'm sorry, I just realized I'm confused by something on this page. The H2 is a GCD of a polynomial and T, which is an element of Z mod PZ?
So T can be, it's an element of Z mod PZ adjoint X, and then you divide out the P, right? So the idea is
okay, so it is a polynomial also.
Yeah.
Okay, that's what I was missing. Good.
Okay.
Thank you.
Yes.
So this runs in polynomial time, you said, right?
Yeah.
But the whole thing, finding the entire NM, you said is exponential, right?
So the other way to do it, if you were sort of trying to figure this out the way we had before, that was exponential, and that involved. Like,
but so if you keep doing this, you say you had some ideas for p cubed. At some point, something should be exponential, right? One of these things should be exponential. One of these algorithms should be exponential, right? Because they can't all be polynomial, right? For p cubed and higher powers of p, right?
Well, does it depend upon the algorithm you're using?
I think he's just said that the particular known algorithm is not polynomial. I don't think they've proved that it's impossible to do it.
Oh, so it couldn't be polynomial.
I think that's what he said.
Right, that's the impression I got.
I mean, so what we have is polynomial, and what we had before for this case was exponential. The thing is, so if you increase the power, like if you look instead for p cubed instead of p squared, I think it should still be polynomial, because what the algorithm, basically the complexity of this basically depends on how fast can you factor polynomials, and so the factoring should be the same even if you look mod p cubed or p to the fourth. So if you're like, I guess, hold on, let me go back to that complexity side. This back here? No, I'm going the wrong way, aren't I? It was polynomial in D plus the size of f plus log p. Yeah. And so the size of f, like, that depends on the polynomial, so that won't change if you go from t squared to p cubed. D was the degree, which also won't change. And log p will be I guess the thing that changes, but it won't change. Yeah, it won't go from polynomial to exponential.
So it's just mine is a silly question, but does it matter to like so I'm always prime p equals 2. Is there any?
Yeah, so generally we like to look at p equals 2 as a separate case when doing number theory because it leads to some problems. Fortunately, this works for p equals 2. Yeah, it works perfectly fine. So that was a nice thing about this. Yeah.
About the Marxist aspect. Like
Can you speak up a little? Sorry.
yeah, sure. Like when you took the modulus of the equation, I was wondering, are there any more properties to that? Like whenever you do something like that, like does it have like a counterpart maybe or something like that?
Does it have a what? Sorry.
A counterpart, or does it just become one other equation?
Oh, okay. So when you reduce it, are you asking sort of when you reduce it mod t, is there like a unique way to do that?
Yeah.
Yeah. So if you reduce everything in the polynomial, it should reduce uniquely, right? I mean, because like the thing is like if we go, when were we reducing things? That was back here, right? Yeah. Okay. Sure. So this is we could write the same thing and change the 9 to like an 18, or like a 27, or like the 6 we can add 9 to it, or like anything like adding 9. That's sort of the identity element, right? When you're working with z mod 9z, it's actually 0, but like that's why. So I mean, the way we do it is generally we keep everything between 0 and 8. Right, so that there's a unique way to do it, but I mean, you could write it in infinitely many ways if you just keep adding multiples of 9 in the right places.
Thank the speaker.